Unit 13B will be a continuation of our conversation about wave optics. So light behaves like a wave. This means that it has a wavelength and a frequency, and it will obey superposition. Last class we learned that light is a wave that travels with a speed equal to the speed of light in a vacuum. This wave can have a wavelength and a frequency. We also learned about how the wave speed would change depending on which medium the light was traveling in. In a vacuum, the speed of light is 3 times 10 to the 8 meters per second. But in any other medium, the index of refraction will cause for that light to slow down in the medium. We actually find that the wavelength of the light in the medium is what changes when its speed changes. The frequency of the wave is strictly set based on the source that is outputting those waves. So when a wave enters a new medium and slows down, its wavelength will correspondingly go down. And this means that the wavelength of light in a medium and the medium's index of refraction are related. And we can use this equation in the bottom here to determine what the wavelength of light will be in a specific medium based on that medium's index of refraction and what the true wavelength of the light is being emitted from the source. This whole idea about light being a wave was actually a very serious debate between Isaac Newton and Christian Huygens. Newton believed that light was a particle, meaning that it traveled in a straight line and it could bump into things like the doorway or the windowsill and it would be blocked, creating a shadow. This understanding of light makes a lot of sense, and it's very consistent with our macroscopic understanding of light. But Huygens proposed that actually light was not made up of particles, and instead light is a wave itself. And the only way that we could prove if light was a wave was if it obeyed laws and demonstrated phenomena that were characteristic of waves, like superposition, interference, or diffraction. In the end, we find that light does behave as a wave indeed, and we call this the wave theory of light. Huygens Principle is basically a way of understanding waves, which says that each point on a wave essentially acts like a source of another smaller wavelet. If every single point on a wave creates its own little tiny spherical wavelet, we can see that those individual wavelets always add up to have their wave front be at the edge of the wavelet, and this essentially describes how light travels. For example, if we sent a beam of light toward this small hole and we only let a small little bit of the light through, we would see that the light would spread out in a circular fashion. This is the wavelet coming from just this individual point. And if we had every single one of these points open, we would have many, many circular wavelets that would add together to essentially create the wave fronts that you see on the left here. And as a wave enters through some kind of opening, it typically spreads out into that opening. But this is a little different between light and other waves. For example, with light, when we have a doorway that's open, the light will only enter where the doorway opening is, and then it will not spread out and fill the room. There will still be a shadow, specifically where the light does not hit. Now this is different for other waves, like sound. If you have an open doorway and a sound wave is entering through that doorway, it's not like there's a shadow of sound anywhere. The sound spreads out and enters the entire room and fills it. The reason this happens is because sound has wavelengths that are much closer to the actual length of the opening itself. So if we can shrink down a doorway opening to be just a very small slit, so we can only let a small amount of light waves through, then we will see that light waves also do this bending. The bending of a wave around an edge or obstacle is called diffraction. And if that opening gets smaller and smaller and smaller, the effects of diffraction are more and more noticeable. On the left here we have light waves entering through a doorway, and we can see that there's a small amount of bending here. And as the opening gets smaller, the degree of bending the diffraction becomes more significant until we have a very small opening, and now the light waves bend and create these circular shapes rather than a straight path like you would have seen before that would have created a shadow. For example, here you can see light waves filling a room. There's a slight bend on the two edges, but mostly in the path where the light is traveling, it just travels in a straight line and lets light travel there. There are several major types of diffraction, and the most common one is called double slit diffraction. Double slit diffraction occurs when we let light pass through two very small narrow slits, and you might expect for the shadow on the opposite end of these two slits to just have two vertical lines, sort of like the shape of the opening that the light is traveling through. But actually we get something different. We get several vertical lines all lined up together. And we call this an interference pattern. There are bright spots and dark spots that the light creates as it passes through those openings and as it experiences diffraction. This experiment was basically what proved that light is indeed a wave. As the light waves travel through both of those two different slits, each slit acts like its own source of small light wavelets that will travel out in a circle. And so if the top and bottom slits each let circles out, you will see that there are points where the two circles overlap, their wavefronts are perfectly aligned, leading to constructive interference, and then there are other spots where the wavefronts are anti-aligned, experiencing destructive interference. As these two slits let light through, we will create an interference pattern sort of like what you see here. Here we have a red laser being shined through only two slits, but it creates these many lines that have bright spots and dark spots. The bright spots are where there's perfect constructive interference. We call those bright fringes or maxima, and the dark spots are where there's perfect destructive interference. We call those dark fringes or minima. So here you can sort of see an example of double slit diffraction. We have our laser light coming in, we have our two openings here, and the way that the wavelets travel out, just because there are two different sources, each with circular wavelets traveling from them, we get this pattern here, where along this line we have a very bright spot with wavelets adding together with constructive interference, and then right next to that we have a little line that is a dark shadow where we have perfect destructive interference and the waves do not add together. They cancel each other out. And then the next bright spot occurs, and then another dark spot, and then another bright spot, and so on. And that interference pattern will happen for a double slit diffraction situation. We call the center bright spot the central maximum, and this will always be the brightest. It'll have the most intensity. And then any spot beyond that we call the next fringe, either a bright fringe or a dark fringe. We can calculate where our bright fringes will occur, at what angle they will be deflected from the central maximum, using this diffraction equation, d sine theta equals m lambda. If you can plug in integer values or 0 for this m number, depending on the wavelength of your light that you're shining through and the distance between your slits, you can predict what angle each bright fringe will be deflected at. We can do the same thing for dark fringes with destructive interference. The only difference is that we add a little 1/2 to that integer m value. So again, d is the distance between the two slits, theta is the deflection angle from the central maximum, and m we call the order of interference. It will tell you which bright fringe or dark fringe you are at. The central peak has an m of 0. And then if you go one above the central maximum or one below the central maximum, that will correspond to an m equals +1 or an m equals -1, depending on which way you go. And then as we go out to farther bright fringes, we step up in our order of interference number. Another type of diffraction other than two-slit diffraction is called multi-slit diffraction, where we can use something called a diffraction grating that has many slits in it. If we shine light through a diffraction grating, we will see that it gives an interference pattern. You can see a diffraction grating right here, and you'll notice that it is often given the number of lines per millimeter of the diffraction grating. And so if you invert this, you can figure out what the spacing is per line for some diffraction grating, and that will be your D number for this diffraction equation. Another difference about multi-slit diffraction is that instead of just creating a bright and a dark spot, it actually creates rainbow fringes. It separates light into its component wavelengths so that we actually get bright fringes that appear as rainbows with different colors. You'll notice that the order of the colors is symmetrical for these different bright fringes. So to get a bright spot, you solve for it using the diffraction equation. And actually, diffraction gratings are what is responsible for a variety of very beautiful and interesting phenomena in the world, like the multicolored nature that you see on the back of compact discs, many iridescent snakes or gemstones demonstrate diffraction. These butterflies and peacock feathers also demonstrate structural coloration, which is essentially an effect of diffraction. The last type of diffraction that we will cover is called single slit diffraction. Actually, if you just shine light through a single slit that's at a very narrow slit width, we will get a diffraction pattern on a screen that is some distance from the slit. You'll see that our pattern has a central maximum with a bright spot, large intensity, and then dark fringes right next to that central maximum with bright fringes alternating from there. In this single slit diffraction equation, we actually solve for the dark fringes in this one. The destructive interference spots can be solved for using this diffraction equation where capital D is the width of your slit. So that'll cover everything for Unit 13B. I'll see you in the next one.